Hey space aficionados, strap in as we embark on an interstellar escapade with the James Webb Space Telescope, our space librarian that's unraveling the universe's most gigantic puzzles, gas planets. These aren't your average rocky neighbors. They're colossal, mysterious, and utterly fascinating, with atmospheres that are just mind-boggling. James Webb Space Telescope is peering into their enigmatic hearts like never before, using its cutting-edge tech to spy on their stormy weather, majestic rings, and maybe even secrets we've yet to imagine. Think of it as the ultimate space sleuth, uncovering clues about how these giant worlds form and evolve, and possibly reshaping our understanding of the cosmos. So, are you ready to dive deep into the gas giant's mysteries with the most advanced telescope ever built? Let's get starstruck together as we explore the wonders James Webb Space Telescope is revealing. Some of the senior researchers thought that it would never be possible to do this, but with some more rigorous tests for a few months, we confirmed that we have done it. It could be argued that one of the most perplexing aspects of our solar system is the fact that not every planet is a nice, solid rock like Earth. Some are literally almost entirely made of gas. You can't exactly stand anywhere on Jupiter unless you manage to fall all the way through its gaseous layers and survive an unreal amount of pressure before making your way to the orange-streaked world's potentially rocky core. That doesn't sound ideal. Even sci-fi video game creators sometimes struggle depicting what it'd be like to traverse one of these worlds. The first thing I tried to do after getting some free reign in the Xbox game Starfield was land my ship on its simulated Neptune, just to see what would happen. The game wouldn't allow it. Needless to say, the mystery of massive gas orbs is a highly intriguing one for scientists too. And now that they have the James Webb Space Telescope's incredibly powerful infrared eyes available, they're putting the spaceborne instrument on the case. Just last week, one team announced it may have some updates on the dynamics of gas giant formation, thanks to the James Webb Space Telescope. More specifically, the researchers say they've started making headway in answering the question of how long gas giants likely have to form around their host stars before all the gas around those stars fades away. The team used the James Webb Space Telescope to probe what's a little confusingly known as the disk wind. This doesn't really refer to a wind like you may imagine. Rather, it refers to the process of gas leaving a disk around a star. This disk would be one filled with different types of material with the potential to give rise to planets. It's thus otherwise known as a protoplanetary disk. We knew that they exist and that they might play an important role in disk evolution. Naman Bajaj, lead author of the new disk wind analysis and a scientist with the University of Arizona's Lunar and Planetary Science Laboratory, told Space.com. What we didn't know was the underlying physics and consequently how much mass is being lost. These are key to answering all our questions on its impact. Such a disk would include non-gaseous debris too, to be clear, like dust that can come together over time to create rocky planets. That's actually how Earth is believed to have formed once upon a time. On the name, I can only suspect that it's because of its slow speed, Bajaj said. The disk when studied by the team, he explains, appears to move at a rate around 10 to 15 kilometers, 6 to 9 miles per second. Fast-moving gas patterns, on the other hand, are typically referred to as jets. These can boast speeds above 100 kilometers, 62 miles per second. Though Bajaj and fellow researchers didn't come up with a final, tightly confirmed answer as to how long gas planets may have to form before protoplanetary disk gas depletes fully, he did offer a ballpark based on his calculations. Considering the gas mass in this disk, and assuming that the gas will keep leaving at this constant rate that we find, about one moon mass every year, it will take approximately 100,000 years, he estimates. Yes, that sounds like a long time. But as Bajaj emphasized, it's an incredibly short timescale in astronomical terms. A protoplanetary disk lives for about 5 to 10 million years. How to find a space disk? The first step in tackling disk wind movements is simply to find a disk wind subject. And to find a disk wind subject, you need to find a protoplanetary disk, of course. Our solar system won't work for this kind of analysis because all our planets are complete, gassy ones included. Thus, the team's disk wind target ended up being one associated with the disk around a young, low-mass star called T-Cha. Honestly, this is a star that's super interesting in its own right. The sparkling body, which lies about 350 light-years from Earth, is known to have a large dust gap in its disk. This dust gap is exactly what it sounds like. These gaps are thought to be created by planets as they consume all material in their way while they go around the star, Bajaj said. Therefore, such a gap suggests the star indeed has budding planets around it and is old enough that those nascent worlds had time to eat away some of the disk itself. We also call this the transition stage, Bajaj said. It is transitioning from a protoplanetary disk to a more solar system-like structure. Furthermore, previous ground-based observations, Bajaj explains, had suggested there's neon in the disk that essentially marks how the disk's gas is slowly headed out. More on that shortly, so an excellent disk subject was in hand. The next step was to start making some observations to see what's going on around T-Cha. It was time to track some neon, gaseous nobility. Neon is a noble gas, which is a category of elements represented by atoms with fully filled outer electron shells, or valence shells. Simply, because of that valence shell feature, these gases are very unreactive. However, it's still possible for them to lose one of those outer electrons if exposed to a high enough temperature. If that were to happen, the gas would become ionized, or electrically charged. Because electrons have a negative charge, losing one makes a previously neutral atom a little more positive. Getting an extra electron would similarly make a previously neutral atom a little more negative. But importantly for astronomers, when ionization in this way happens somewhere in the universe, a signature is left behind that can be tracked by their equipment. This includes the James Webb Space Telescope. And, as Bajaj explains, neon's signature is particularly special for disk wind tracking. First off, some gases are just more likely to exist in protoplanetary disks. The lightweight neon is one of them. For heavier noble gases, their abundance is very low, so we wouldn't see them, Bajaj explained. Second, ionization happens differently for different elements. Sometimes, there needs to be a really high temperature involved to kick an electron off an atom. Other times, the electrons exit more willingly and do so at lower temperatures. Helium, which is much more abundant than any of these noble gases, has a much higher temperature requirement for it to get ionized, Bajaj said. Yet neon, on the other hand, will spit out an electron under more modest temperature requirements, which is why the team looked for specifically neon emission lines to see how the gas evolves within the T-Cha protoplanetary disk. In short, they found two. When we saw the spectrum for the first time, my first week of grad school, we saw that both the neon lines were booming, Bajaj remarked, adding that one of those lines had actually never been seen before around T-Cha. We figured out that neon is coming from further away from the star by looking at it with James Webb Space Telescope. I spent many months trying to figure out from the images whether we can see the neon emission structure. It was very hard, Bajaj said. It took about 8 months, he explained, before he could confirm from James Webb Space Telescope images that the structure was actually there. But that's not all. There was a surprise. Along with the neon lines, the team found a very strong argon line, Bajaj said. Though an argon line like this had been seen in a few protoplanetary disks before, none had appeared quite this strong. Then, there was another surprise. We always thought that we had 2 neon emission lines and 1 argon emission line, but one fine day I was going through the spectrum and found that we have another argon line, Bajaj said. This was much weaker than all the others, so we missed it for quite some time. We realized that this is the first time we are seeing this line in any protoplanetary disk, he added. Some of the senior researchers thought that it would never be possible to do this, but with some more rigorous tests for a few months, we confirmed that we have done it. Where do we go from here? A major point Bajaj reiterated was that the team's new result is really one small, albeit crucial step in the grand march of understanding more about the mind-bending nature of gas planets. Where do these strange spherules of gas come from? Their architecture seems so hard to contend with. Not only does the new work strengthen many previous observations conducted in this domain, some of which were led by Bajaj's co-authors in fact, but it also opens the door to a breadth of fascinating future studies. With these disk-wind details in hand, for instance, Andrew Selick, co-author of the study and a postdoctoral researcher at Leiden University in the Netherlands, put together a subsequent paper outlining simulations that suggest the disk wind process is driven by something called photoevaporation. At the risk of oversimplification, photoevaporation in this case refers to energy from a star heating up gas in the disk around it, which then forces that gas to disperse into space. Much like how water gets evaporated on Earth, Bajaj said. Selick's paper was actually recently accepted for publication in the Astronomical Journal. A preprint is available to view just here. Okay, at this point I may be musing a little, but after getting so deep into the dynamics of the disk wind, I can't help but consider how satisfying the subject is. It's almost like the pieces simply fall into place. For instance, because of the way gas seems to exit a protoplanetary disk, it's true that once the gas is gone, only rocky planets can form. It's also the case that gas worlds, and in particular gas giants, are more likely to pop up in the outer areas of a planetary system. There tends to be more general mass in the outer regions of a protoplanetary disk, therefore leading to more massive planets as a whole, which would include Jupiter-esque gas giants. Plus, host stars themselves have a say in the matter. Rocky planets very close to the star will have very little or no atmosphere, like Mercury, as it will be stripped away by the sun's high-energy photons, similar to photoevaporation, Bajaj said. For gas giants, if they happen to form close to the star, it is possible that they find a balance between their gas and the sun's energy. And finally, though it's severely cliché to say at this point, all of this is a testament to how much the James Webb Space Telescope is revolutionizing our understanding of the universe. Its infrared sensitivity is immense for sure, but a lot of its discoveries owe themselves to the body of work already available to build on. The library of papers that's been helping scientists decide where, precisely, the James Webb Space Telescope should look. We really do stand on the shoulders of giants and giant telescopes, Bajaj said. The study was published on March 4th in the Astronomical Journal. And there you have it, cosmic voyagers. We've just skimmed the surface of the vast ocean of secrets that the James Webb Space Telescope is uncovering about the gas giants. It's like we've been handed the ultimate cosmic key, unlocking the mysteries of these enormous swirling worlds that have baffled astronomers for centuries. As James Webb Space Telescope continues to beam back its treasure trove of data, who knows what astonishing secrets we'll uncover next? Will we find new moons, uncover hidden rings, or perhaps reveal processes that challenge our very understanding of planetary formation? The possibilities are as boundless as the universe itself. So, keep your eyes on the stars and stay tuned for more revelations. The journey with James Webb Space Telescope is far from over. In fact, it's just getting started. Until next time, keep marveling at the wonders of the cosmos, and remember, the universe is always ready to amaze us with its endless mysteries. Clear skies, everyone.